My name is Marinos Stilianou. In this video, we will go over the steps for exporting finite element analysis matrices and vectors from S-frame and how to properly interpret the output. The option to export a finite element analysis matrices and vectors to the trail file is only available with academic licenses. So if you're not a student or a professor, then you probably do not have this capability with your commercial license of S-frame. The export of the finite element matrices is done through the trail file, and we will see in a few minutes here the option that you need to select. And it's done while the solver is running an analysis. Now, this is the analysis window in S-frame. So you can run a linear static analysis if all you want is the stiffness matrices. You could run an unstressed vibration if you want both the stiffness matrix and the mass matrices. And you could run a p-delta backlink if you're interested in seeing the stiffness matrix and the stress stiffness matrix. And oh, by the way, you can run any other analysis as well, and you'll get slightly different combination of matrices in the trail file. But those three are the most basic, I would say. But what you will definitely need to do is to select the last option of the solution trail detail. So this is the maximum detail that you will get in the trail file. The option plus FEA matrices and vectors. I made a note here that ignore errors. Well, we never actually give this advice to anybody, but if you have a model and you build it, let's say, with all the proper sections, section properties, material properties, etc., but you haven't really defined the loads, for example, and you run a linear static analysis, you're going to get errors, right? That there are no loads to solve the displacements for. Now, if all you're interested in is the stiffness matrix, you can ignore that message. So you can ignore errors. S-frame will still export the matrices, okay? But you need to decide whether the errors that are reported are okay with you. We will be using a simple 2D structure in this video as an example. And this simple structure is used in another training video about S-frame. This structure has 21 elements. It has 12 nodes, and each node has 6 degrees of freedom per node, which basically tells us that the maximum degrees of freedom in this structure is 12, the number of nodes, times 6 degrees of freedom per node, which is 72. But we know that if we don't constrain the structure, this will be unstable, meaning that if we apply any loads to this structure, it will just move as a rigid body. And that's why we apply boundary conditions at the supports here. But also in this case, we will apply the default 2D constraints, which basically constrain every node from moving in the Z direction, which is perpendicular to the page, as well as constrain not to rotate about the global X and the global Y axis. So if we do some simple arithmetic here, we started with 72 degrees of freedom. We applied the 2D default constraints, which is 12 nodes times 3 degrees of freedom being constrained at each node. Then we subtract 2 being the 2 constraints at node number 2 or joint number 2. This joint cannot move in the X or Y. It can only rotate about the Z axis. And then one additional constraint at joint number 1. This joint is not free to move in the global Y direction. And this leaves us with 33 degrees of freedom for this structure. Before we leave this slide, I'd like to point out that these arrows that you see in this graphic indicate the local x-axis for each element. And as you can see, they can be going from any direction to any direction, really from, in this case, it goes from node 5 to node 6. In this case, it goes from node 1 to node 2. And then the crossbars, again, you can see the direction of the local or element coordinate system. The global coordinate system is the one in red here, X, Y, and Z coming out of the page. In finite elements, we form element matrices and element vectors. Then we transform the coordinates to global, and then we assemble them to get the system matrices and vectors. Finite element analysis and structural analysis software like S-Frame internally renumber joins. And that is necessary because the user could choose any name for a joint. So when you build this structure, you don't have to start from joint number 1 and go to joint number 12. You could say for the first floor, I'm going to use numbers like 100 and 101. For the second floor, 200 and 202, or 5 or whatever. So the program has to renumber them internally for internal purposes in order for them to be consecutive numbers. And in addition to that, it has to optimize the numbering so that the storage requirements in the program can be minimized. And S-Frame does that. And this is an excerpt from the trail file. And you will see the old numbering, meaning the user numbering, and this being the new one, the optimized, that is used internally by the finite element analysis program. Trail files can be really long for realistic structures. Hundreds of thousands of lines, even millions of lines in the trail file. By the way, the trail file has the same name as your model. However, the extension is .trl for trail. Because the trail file can be so long, we inserted unique strings throughout these files to make it easy for you to search and locate what you need. So this string here, for example, matrix vector printing, will show at the beginning of every section where we are actually printing a matrix or a vector. So you can search for part of this string, for example, matrix/vector printing, and it will take you to the beginning of printing a matrix or a vector. More specific searches can be done for the element matrices. For example, if you're looking for the element stiffness matrix in element coordinate system, then you search in your text editor for this string here. If you're looking for the element stiffness matrix in global coordinate system, you search for this string. And by the way, if you're also printing out or exporting the mass matrix, then the only thing that you need to replace here is element mass matrix in element coordinate system. If you exported the stress stiffness, you just replace the word stiffness with stress stiffness matrix, etc. Now, the element stiffness, mass, stress stiffness, etc. matrices are symmetric. So S-Frame will only print the lower triangular part, as we will see very shortly. The element transformation matrices, these are the ones that transform from element coordinate system to global coordinate system. These ones are full matrices. They're not symmetric. So you should expect to find the full 12 by 12 matrices in the trail file. This is an excerpt from the trail file, and it is for element number 1, as you can see here. The element stiffness matrix is 12 by 12, but since the matrix is symmetric, we only print the lower part. The element transformation matrix, on the other hand, is also 12 by 12, and since it is not symmetric, we print the whole 12 by 12 matrix. The next step in all finite element analysis programs is to convert or transform the element matrices to the global coordinate system by performing this matrix operation here. And we have the transformation matrix, we have the stiffness matrix in element coordinate system on the previous slide in your trail file. So if you're so inclined, then you basically perform this operation and you will get this matrix, which is again symmetric. So all we print is the lower triangular matrix. As mentioned earlier, because the solver renumbers the joints, you will need some additional information in order to interpret the system matrices and vectors. And that is in the form of a table, and we refer to that as the degree of freedom mapping table, which you can see here. There are quite a few columns here, and in fact, there are some that are redundant. So at some point, we will probably clean this table up a little bit. But let's just focus on these columns that are marked by the red boxes for a few minutes. So the user node number is what you selected as the join numbers of your structure. So these will be the ones actually that you will see in the graphics window or in the spreadsheet window in S-Frame. The new is the renumbered, and this is sequential, as you can see. And then we have this table here, which is actually the one that gives us the degree of freedom mapping. So what this tells you is that for your node number 2, which is this one here, degrees of freedom 1, 2, 3, 4, and 5 are prescribed to 0, meaning I cannot move in those directions. But rotation Z is free. And that is the first degree of freedom in your system matrices and vectors. Okay. The second row here tells you that for your joint number 1, it can move in the X direction. It cannot move in the Y, the Z, the rotation X, rotation Y, but it can actually rotate about Z. And this is the second degree of freedom, and this is the third degree of freedom. And then it goes through all the other joints. And if you remember, we applied the 2D constraints, which basically constrained all the other joints so there is no displacement perpendicular to the page. And then there is no rotation about the global X and the global Y. So that's why these are all zeros. And then the rest, again, it gives you basically the row and column number for that degree of freedom. So if we go to your joint number 7, and if you're wondering which row and column corresponds to the displacement in the Y direction, then you'll find it right here, the 20th. Okay. Okay, we're almost ready to look at the system matrices now. Now, the system matrices in S-Frame are stored in sparse storage format, and S-Frame will only print the non-zero entries of the system matrices. So it doesn't waste storage for the zero entries, basically. Please note that these matrices are printed or they're formed and made available in the trail file after the boundary conditions are applied, which means that if you go back to the previous slide where we have or show which degrees of freedom are constrained with the zeros in that table, those degrees of freedom are removed from the system matrices and vectors. To locate the system stiffness matrix quickly, just search for this string. And by the way, we'll also show how to import into Altair's Compose or MATLAB. So this is a graphic representation of the sparse storage scheme. So imagine that you have a system matrix like this. It's symmetric, so we should only be concerned about the lower triangular. The way that S-Frame stores this and makes it available in the trail file is starting from row number 1. If the first entry is non-zero, then it will write it in the trail file. Then we'll move to the second row, and it will again write all the entries that are non-zero all the way up to the diagonal. Row number 3, you can see it begins with a 0, so we'll skip that, and we'll go to row 3, 2, column 2, and we'll enter the value there, and so forth. And this is used on not only for stiffness matrix, but for the mass matrix and the stress stiffness matrix as well. Again, this is from the trail file. You can see the way that S-Frame writes the information about the entries of the stress stiffness matrix. So there are 161 non-zero entries. Now compare that number to the number of entries that the solver would have to store and operate on if we dealt with a complete matrix, which, if you remember, it was 72 by 72, which is like more than 5,000 entries. So the storage savings are considerable, but more importantly, the execution or the solution becomes a lot faster by using this storage scheme. By the way, if you look at this text here, which gives you the stiffness matrix, you'll probably notice that this is correct syntax to copy and paste in programs, in actual source code. If you ignore, all these spaces, right? So each one of these lines is again correctly program or formatted so that you can copy it in a C program or Fortran or MATLAB or the Altair Compose, which is the equivalent to MATLAB. We wrote a couple of template functions to convert the matrix that is in the trail file to a regular full matrix format. So it starts by initializing an n by n matrix. Right here between lines 6 and 10, you should copy and paste the stiffness matrix or mass matrix that you have in the trail file. So you just copy and paste it over here. And then what the program also does then, it copies the lower triangular part of the matrix to the upper triangular, and you basically then end up with a matrix which is what you are used to, a full matrix storage scheme. Last but not least, the system load vector. So search for writing global load vector. This table gives the loads at each node. Please note that the node numbers are the user node numbers. We are being a little bit inconsistent here. And again, this is something that we probably need to address in a future version. Okay, so there is only one load in this model. It was at join number 12. And if you remember, join number 12 was not renumbered. It was join number 12 in the user numbering scheme, and it was still join number 12 in the optimized one. So you can see here, join number 12, it has only one non-zero value in the x direction. As you can see in S-Frame as well, you have your load in the global x direction, and the value is 8. This brings us to the end of this video. Thanks for watching, and I hope that you found it useful.